Question 2. A deep sea diver is working at depth where the pressure is 3 atmospheres. He is breathing out air bubbles. The volume of each air bubble is 2 centimeters cubed. At the surface, the pressure is 1 atmosphere. Find the volume of each bubble when it reaches the surface. You may assume the temperature is constant. So what's often useful to use is what's called the combined gas law. So as well as the equation PV is equal to nRT, we can picture a situation where we have 2 states of a gas. So we might say P1 V1 is nRT1 and P2 V2 is nRT2. So P, V and T have got the subscripts because they can change. N and R are constants in this case that won't change. The amount and the gas constant we're going to say is constant. In other words, nR can be equal to P1 V1 over T1, and it can also be equal to P2 V2 over T2. So without the nR at the start, let's just rub it out, this becomes what's called our combined gas law. We can put in initial and final states. And then we could further simplify this because of the statement that the temperature is constant. T1 and T2 are the same. So we could go even further here and say in this particular question, it's just P1 V1 is equal to P2 V2. This is back to the original form of Boyle's law, and you might have just jumped straight to using Boyle's law. So this is the equation we're going to use. The second thing we might think about here is units. Now, provided the units are the same on both sides of our equation and the units are absolute, it doesn't particularly matter what units we use at this stage. Now, the only unit that we're going to use that's not absolute really is for temperature, and that doesn't come in here. So we don't actually need to convert any units in this question. So we might just write that we're trying to find the final volume. So from this form of the equation over here, I'm going to come and work over here. V2 is equal to P1 V1 over P2. So P1, the initial pressure, is 3.0 if we're working in atmospheres. The initial volume is 2.0 if we're working in centimeters cubed. And the final pressure, P2, is 1.0 atmospheres. So this means, nice and easy, we can just say the volume is 6 centimeters cubed. If you were working in meters cubed, then of course we should remember that a meter cubed is 100 centimeters by 100 centimeters by 100 centimeters. So it's 1,000,000 centimeters cubed is 1 meter. So this could also be expressed as 6.0 times 10 to the minus 6 meters cubed. Part B, the temperature actually increases as the bubble rises. Explain using the idea of particles what effect this will have on the bubble volume when it reaches the surface. So when we're thinking about particles in the particle model, the particle speed is dependent on temperature. So we could say that at a higher temperature, the particles will travel faster. So if they're traveling faster, then we might be tempted immediately they'll hit the sides more often and they'll hit the sides harder. But actually this would be wrong in this case because we know when the bubble reaches the surface, the pressure is 1 atmosphere. So we can't say the pressure is going to get bigger because it's going to arrive at the surface at atmospheric pressure. So we can't just increase the pressure. So instead, we're going to say the bubble expands even more. So the bubble expands further. So it'll be bigger than 6 centimeters cubed. So And the idea here is that the particles are going to hit the sides less often. And they need to hit the sides less often because they are hitting the sides harder. So the pressure is 6.0 centimeters cubed. Sorry. So the pressure is 1 atmosphere, even though the particles hit the sides harder. So their increased distance between the bubble walls mean the particles have to travel further. They hit the sides less often. So even though they're hitting the sides harder, the pressure can still be 1 atmosphere in this particular case.